let us revisit equivalence classes and observe a couple of interesting relations between the set of equivalence classes and the underlying set. Suppose the set is 1, 2, 3, and if the relation R is say 1, 1, 2, 2, 3, 3, then the equivalence class of this one is 1, equivalence class of 2 is 2, equivalence class of 3 is 3. If the relation is along with 1, 1, 2, 2, 3, 3, suppose we have 2, 3 and 3, 2, then equivalence class of 1 is just 1 itself, and 2 is 2, 3, 3 is 3, 2 or 2, 3. And if the relation is A cross A, then equivalence class of 1, 2 and 3 are one and the same. We saw many interesting properties that if you look at any two equivalence classes, they are either same or intersection is empty and such things. And you find B in A, then you see that A in B. Now you look at the set A equals 1, 2, 3. This one is trying to represent A like this 1, 1, 2, 2, 3, 3. That relation is trying to represent the set like this. Okay, let me call it as A prime. And this one is trying to represent 1 and then 2, 3. Over here, A prime is trying to represent A like this. So what is this? This one is partition of A. This one is also a partition of A. This one is also a partition of A. What do you mean by partition? You have a set A. You rewrite that set as A1, A2, so on up to AK. So in this case it is A1, A2, A3. In this case it is A1 and A2. In this it is A1 alone. You write A as A1, A2, so on up to AK such that union A1 union A2 so on up to union AK gives you the underlying set. You take the union, you get A. Take the union, you get A. Take the union, you get this. Most importantly, you look at any two sets AI, AJ, their intersection must be empty. You look at A1 and A2, intersection is empty. Look at A2, A3, intersection is empty. A1, A3, intersection is empty. A1, A2, intersection is empty, union is A. And you have just one set. That's precisely partition. For example, if my A is 1, 2, 3, 4, then a possible A prime is 1, 2 and 3, 4. Or I can also write 1, 2, 3, 4. I can also write 1, 2, 3, 4. So this tells you that the set of equivalence classes partitions the underlying set. The set of equivalence classes of R or A, anything is fine, because partitions the underlying set or partitions the set A. So this also tells you other things. We also observe that set of equivalence classes and the underlying relation, they have one-to-one mapping, meaning given an equivalence relation, one can construct this. Given this, one can construct this. And from this we observe that this gives you set of it gives you the partition of the underlying set. So maybe in the counting problems this relation may be of use. Trying to count this or this or this, maybe they are related. Yes, it is indeed true, and which we use in when we count number of equivalence relation and so on. We shall highlight that now next. The question is this: given a set 1, 2, 3, we ask how many different equivalence relations are possible. Since there is a one-to-one correspondence between the set of equivalence classes of A and the underlying equivalence relation, so counting this is equivalent to counting number of different equivalence classes of A. Okay, number of different, the set of equivalence classes. We also observe that equivalence classes partitions the underlying set, which means counting this is equivalent to this, in turn this is equivalent to number of partitions of A. So you look at A, which is 1, 2, 3. One partition tells you 1, 2, 3. The next partition tells you you place 1, 2 and 3. Fine. Now this partition gives you the equivalence class 1, 2, 3. This one gives you the relation R equals 1, 1, 2, 2, 3, 3. This connection is what we wanted to bring it out through this lecture. This tells you that 1 is 1, 2, 2 is also 1, 2, and 3 is 3 alone. The corresponding relation is 1, 1, 2, 2, 3, 3, 1, 2, 2, 1. So listing, so this one is different from this. So listing all possible equivalence classes is equivalent to listing all possible equivalence relation is equivalent to listing all possible equivalence classes. In turn, that is same as listing all possible partitions of A. Now, if you can count this, we indeed get a counting for this, which represents the count of this. So there is an interesting number called Bell's number, denoted as Bn. That tells you how many different equivalence relations are possible. So the details about this, and we will discuss as part of problem session. You can also refer my scribe where this number, the expression for Bn is given, how it is arrived at. So the detailed explanation is given there. But one should understand this interesting relation between partitions and the set of equivalence classes followed by equivalence relation. So when we were discussing mathematical abstraction, mathematical modeling, this is something I was highlighting. So objective is to count this. We model this problem as this. Subsequently model this problem as this. But when we count this, this number indeed represents the count of this, count of this. Counting directly or listing all possible equivalence classes or equivalence relation is not straightforward. Rather, we do this modeling and followed by counting or listing via this approach. And that's precisely the focus of this course. Mathematical abstraction followed by modeling. You either approach the problem in the given domain itself, for example, in the context of relation itself, but when you know that that direction of research may not give you desired result or that may not be a promising direction, then we try modeling that problem as something else similar to counting equivalence relations. And subsequently we experiment, can we count this? When you know that even that direction is not promising, model that to a different domain. So there is no thumb rule, but depends on the case study and the problem that we work with, the abstraction, modeling, what kind of modeling one should do, and which is the right model, appropriate model for this problem, that comes by practice. This course will teach you many case studies, and through that you will be trained to think, abstract, model computational problems that you come across in your research, either in theoretical computer science or system research or application research. We shall discover more as we go through.